The last part of this chapter is about Le Chatelier's principle. This principle is about systems already at equilibrium and how they respond to disturbances. When a disturbance is applied to a system that is already at equilibrium, the system will respond by shifting in the direction, right or left, to the favor of products or to the favor of reactants. That minimizes the effect of the stress. In this sense, stress could be the addition of a reactant or a product, or removal of a reactant or a product. It could also be a change in the volume of the system and a subsequent change in pressure. And also it can be a change in temperature. You are going to learn how each of these disturbances affect a system at equilibrium, and will be able to determine in which direction the reaction will shift in order to re-establish equilibrium. When a substance is added, it could be a reactant or product. The disturbance is now there's too much of that substance. The reaction will respond in a way to decrease that increase. Therefore, it's going to try to decrease it by using it. As a result, the reaction will shift away from the side you are adding to. Let's say to this equilibrium, we are adding nitrogen. Now there's too much nitrogen as opposed to being in equilibrium. Nitrogen must be decreased, and the system can decrease nitrogen by consuming it, using it in the forward reaction. Therefore, the reaction shifts right. The reaction shifts away from the side you're adding to. How about when a substance is removed? What happens then? The equilibrium shifts to increase it by producing more of it. Because the disturbance is that now you got too little of that substance. The system will want to increase it back up. It can increase it by producing it. Therefore, the reaction shifts towards the side you are removing from. If you remove hydrogen from this equilibrium, now there is too little hydrogen. The system will want to make more. To make more of it, it has to shift left. Here's an example. Hydrogen sulfide reacts with oxygen to produce sulfur and water. For each of the given scenarios, we're going to determine whether the equilibrium will shift to the right, left, or neither. We have not talked about what cases the reaction is not going to shift in any direction. Pay attention to the physical states. Remember the equilibrium constant expressions for reversible reactions? They do not include pure liquids and pure solids. Therefore, a pure solid is not going to affect the equilibrium upon its removal or addition. As long as a solid is present, equilibrium is going to stay at equilibrium. It will not be disturbed. So let's see these cases. If you add oxygen, we're adding oxygen to the left side. Now we have too much of it. It needs to be decreased by being consumed in the forward reaction, and the reaction will shift to the right. How about removal of hydrogen sulfide? If you remove hydrogen sulfide, the system will want to make more of it. By shifting towards that side, the reaction will shift towards left. If you remove water vapor, that means you're removing from the product side. The system will shift towards that side to make more of it. It will shift right. How about the addition of sulfur? Because sulfur is a solid, it will not affect the equilibrium, and its addition is not going to cause a shift. Now be careful if the statement says removal of sulfur, because it depends on how much you remove. As long as you don't remove all of the sulfur, it's not going to affect the equilibrium. But if you remove all of the sulfur, all of it, then there will be no sulfur to facilitate the reverse reaction, and the reaction then will shift to the right. But for that to happen, all of the solid product, sulfur, must be removed. Now decide which direction this reaction will shift based on the disturbance. In this problem, you're also asked to determine the shift in the equilibrium upon a disturbance. But also there's a comment about the value of Kc. You got to remember, Kc changes only with temperature.